Hello, welcome to MTC's SCADA Lab channel. My name is Jeff, and in this video, I'm going to demonstrate how to monitor and control electric substation equipment at a small scale. My primary project goals were to 1. Program remote terminal units, also called RTUs, for control of Modbus communication protocol. 2. Create a human-machine interface, or HMI, that presents all data and enables all commands necessary for a user to understand all relevant statuses and intuitively operate the system. And 3. Integrate two types of RTU to show basic input-output functions, or I/O, using Modbus with control from an HMI. These tasks required mapping network infrastructure and including safeguards in the HMI to account for different levels of user permissions. The scenario this project emulates is monitoring and control for an electric substation utility, mostly from the perspective of an HMI operator. There are aspects of this scenario which account for safety practices between HMI remote operators and field personnel as well. Our primary technical goal is to control and monitor motor-operated switch positions. One reason you might want to do this is to shift which power conducting lines in the substation take power so that utility personnel can conduct maintenance on equipment, or because equipment on a powered circuit experiences a casualty and the utility wants to maintain power for their customers. The operator can also track the state of locally operated manual switches based on reports from field personnel. The remote operating station also tracks alarm conditions such as availability of power feeds, state of circuit breakers, and loss of power to the customer. In the rest of the video, you will see the following material. First, I will point out several life-endangering conditions and quality of service issues in the substation environment. Next, I'll discuss function as the key principles and technology needed to complete this application. Third, I'll post the network diagram for the system. After the network diagram, I'll describe the HMI. And after HMI, I'll cover several topics that are administrative in nature. This will cover schematics and technological alternatives. There are mechanical and electrical sources for risk at electric substations that affect safety to personnel and equipment, and to quality of service for the utility's customers. The physical motion of motor-operated switches can injure or kill a person who gets caught in the switch's arc of motion, and electric power inside the cabinet can present lethal danger to technicians while they work inside the cabinet. Electricity in the switches themselves poses dangerous voltages and currents, but is outside the scope of my project, which focused on correct configuration of the switch control cabinets. Inside the control cabinets, there are also circuits which can deliver lethal injury if the technician does not observe safe practices. If the technician needs to change terminal wirings, he should remove power from the cabinet with the appropriate AC supply power switch and remove DC power from the batteries by disconnecting the battery circuit jumper cable. If the technician is working inside the cabinet holding on to conductive material like metal tools, he also needs to prevent the material from connecting exposed battery terminals. The last risk conditions I'll discuss are loss of service for the customer and false positive alarms, stemming from incorrect readings of switch states. Certain mechanical settings in the motor control cabinets and communication degradation can cause the HMI operator to receive incorrect information about the current state of a switch. I saw two examples of this while I worked on the project. The first being incorrect alignment of position sensing limit switches, and the second being low battery power for the radio transmitters. Depending on whether a signal comes in as a false positive or a false negative for the state of interest, the HMI could determine that the power is going to the customer when the customer has actually lost power, or the HMI could determine that part of the circuit has a casualty when the condition doesn't actually exist in the field. Now that we've covered risks in this environment, I'll describe technical operating principles in the project. To start this project, I needed first to learn how to use Modbus to communicate between my HMI and field devices. The authority for Modbus principles and functionality is the Modbus Application Protocol Specification, available from modbus.org. For the scope of this project, I needed only to learn the Modbus address format so I could label signals in my equipment with the correct address on an OPC server. The OPC server could then relay values at those addresses between field devices and my HMI. Setting up tags required 4 further steps. 1. Associating the I/O terminals within the RTUs with their Modbus address. 2. Making a channel in the OPC server for Modbus TCP communication. 3. Adding nodes for each of the GE radios and 6net RTU. And finally 4. Listing and configuring each I/O signal at each node. For viewers who are unfamiliar with Modbus protocol, here's a basic description of its communication and addressing scheme. In Modbus, a single master unit, sometimes called a client, polls a number of field devices, called slave or server units. Polling means that the master unit updates its memory for field device statuses and issues commands to the field devices by communicating with each device one at a time in an ordered fashion. The field device will only transmit information when it responds to a master's pull transmission. This figure shows the way that the master device and field device identify the signal terminals in the field device. My system employs only discrete outputs and discrete inputs, and all of my RTUs use expanded addressing, so they use 6 digits instead of 5. Therefore, all of the addressing needed in this project follows the formats of 6-digit numbers, starting with 0 for tags that are writable and 1 for tags that are read-only. This concludes the function section of this video. Next, I'll discuss network topology. This application requires network devices to communicate status and command signals across different physical media and network domains. I'll start my discussion from the field end instead of the user or OPC end. For my project, field devices are members of a virtual network that the MTC SCADA department head created for radio equipment called 192.168.204.0. That's a CIDR/24 network. As Modbus devices, field transmitters are identified by a parent unit IP address. The master radio in my network has IP address 192.168.204.30. Each corresponding SECO unit then has a label like bracket 192.168.204.30 end bracket .1. I have one other kind of field device, a 6-net VersaTrack RTU, that is currently inside the SCADA lab room and connects to the network with an Ethernet cable. That one is called bracket 192.168.204.29 end bracket .1. The RTU itself is stuck with an IP address on the 192.168.3.0/24 network. So in order to reach it, traffic must pass through a device that applies network address translation from 192.168.204.29 to the stuck IP address at 192.168.3.55. The GE MDS radios and the VersaTrack RTU join the radio network through physical ports on a managed switch that are configured to pass traffic only on the radio VLAN. Any traffic leaving or entering the radio VLAN goes through the radio network gateway at 192.168.204.1. That gateway is one of the ports to the SCADA lab router, which will also route traffic into and out of the main SCADA lab network at 192.168.200.0/22 through the SCADA lab network gateway 192.168.200.1. The only other device of note for this network is the SCADA lab ignition gateway, which hosts my HMI and includes an OPC server that relays tag information between the field devices and the HMI. When I open the Substation HMI on my computer, the application comes from the ignition gateway. Next, I'll show you pictures from my HMI screens and some video clips showing how a user would interact with the HMI. Operator interface is the crux of this project, so we'll cover all the HMI windows here. After logging in, the main operations window is the hub of all other functions in this application. It's important to note the login phase of the HMI because the HMI handles security for this application based on the identity of the user. When users get to the main operations window, every user will see the current status of substation circuits, but their access to monitoring and control functions through the navigation buttons depends on the security role assigned to their user account at the ignition gateway. The predominant graphic feature of this HMI is the substation status diagram. In order to show which conductors are currently energized, I created tags within the HMI design application that use Boolean logic applied to power feed states and switch states. Here's an example of some logic that controls color animation for a conductor in the substation. This window shows the expression that determines if the customer is connected to power. Each of the tags you see here are Boolean tags for switch position, except for J3, which shows if junction 3 is energized. I wrote my logic to represent closed switches as 1s. Now I'll show you the motor-operated switch command window. The primary utility for this application is that it gives remote operators the ability to open and close motor-operated switches. The open and close buttons here do not connect directly to the open and close commands because we need a layer of safety to protect field personnel from the switch arms as they rotate. In this application, I simulate this safety check by referring the operator to a pop-up screen whenever they command a switch to open or close. I'll show you an example of that here by attempting to command switch 2 to open. Here you see the pop-up window, which says, do not select yes if any personnel are within the switch operating envelope. I'll click yes here, and now the command will transfer to motor-operated switch 2. There's another safety feature on this screen which prevents an operator from being able to simultaneously issue an open and a close command. For any switch, the only button enabled for the operator is the one opposite of the switch's current state. Now I'll show you some more of the switch detail and control windows. I'll go to the MOS detail button here that shows the motor operated switch detail window, which is another way to view switch position status as well as information like whether the switch is in local versus remote mode and if the cabinet door is open. Command center personnel would benefit from that information as potential troubleshooting indicators and safety measures. I'll go back to the main menu and show you the manual switches window. This allows an operator to push switch statuses into the HMI which don't have remote monitoring and control. Field personnel can change these switches, and in this scenario, the field team would report such a change so the command center can accurately determine which parts of the substation are energized. I'll show you an example of what the diagram looks like when links become unenergized. It looks like I can isolate this section by opening switch 2225, which I'll do here. Now you see these turn gray, which means that they are unenergized. I'll restore power here and go back to the main menu. Next, I'll show you the simulated circuit breaker and feed status window, which lets the supervisor pose casualty control drills for an operations team. As part of a controlled environment with other safeguards, for example, moving the source for all system tags to a separate information source from the substation's live tags, the supervisor could trip the status of a simulated circuit breaker, testing the command center's response. Here's an example of feed and circuit breaker states changing the energy flow in the substation. I'll remove power from the customer side here by simulating that circuit breakers 1 and 3 have tripped. And now that's gone. Go back to the main menu, and now I'll show you the 6net window. In the 6net window, I demonstrate interoperability with a different brand of equipment from the GE MDS radio using Modbus protocol. I wired this RTU with a single output, which sends its output to a single input on the same RTU because, again, the emphasis here was on interoperability with this different RTU and not to actually interface with field equipment. I'll demonstrate that HMI successfully reads and writes the tags from this RTU. When I click on Output 3 toggle button here, you will see that the output button changes color shortly after I activate it to show that it toggled the output. I'll do that now. Just did it right there. After some delay, the HMI tag for the RTU's input will also update to show the new state of the input. Up next are some windows to show overall system performance and casualties. Here's the historic trend page where operators can see the current state of each motor operated switch. In this case, you can see that at switch 1, I recently sent a command to open, and the switch shortly afterwards confirmed that it had opened. The panel on the far right shows status for feeds, circuit breakers, and the decisive indicator for substation performance, which is service availability to the customer. Next, you'll see the alarms page. Here in the alarms page, you'll see an alarm table that lists which kind of casualty is present, its severity, the time it occurred, and whether it has been acknowledged. The types of alarms that I capture in this HMI are tripped circuit breakers, loss of power feed, loss of junctions, and poor tag quality. Now that I've explained the operating principles and shown the project operating in its intended environment, I'll cover some administrative details for project planning considerations. My system schematics describe wiring inside my SECO cabinets and a 6net RTU cabinet. For my SECO cabinets, the items of interest are the connections between the SECO main distribution board and aftermarket installed GE MDS radios called NetIO modules, which relay system information and commands over a 900 MHz radio signal. The terminal board drawings take up a lot of room and the wiring can be explained without them, so I'm only showing the wiring going to the NetIO modules. Power to both NetIO modules comes from a positive 24-volt DC terminal at terminal block 1, slot 1 in the SECO cabinet and connects to pin 1 at the top left of the NetIO module. And the connection for DC common comes from terminal block 1, slot 2 connecting to the NetIO module's pin 2. Without going into every other terminal connection between the SECO cabinet and the NetIO modules, I'll point out that the base module carries most of the signals, including the digital outputs to command the switch to open or close. The expansion module is in place to provide additional I/O channels, and in this case, it carries the signals that indicate whether the switch is fully open or closed. All termination information for the SECO cabinet terminals is available at the left side of each signal in this diagram. The second set of schematics shows most of the information for my 6net VersaTrack RTU cabinet. The only section missing is part 2 of 2 for the RTU terminals, where two terminals hold the plus 24-volt DC wire and the DC common wire, and the other 16 are left blank. The left side of this diagram shows the incoming power to the cabinet going through a power supply to transform from 120-volt AC to 24-volt DC, going through several sets of terminal blocks to power the Allen-Bradley NAT device and a VersaTrack RTU. I had to put a NAT device in this cabinet because the IP address on the VersaTrack RTU is on a different network than the SCADA radio network, and the RTU model is not supported by its manufacturer's configuration software anymore. Therefore, I couldn't change the IP address to one that's a member of the radio network. The right side ladder shows the only other wiring of interest in this schematic, showing that I run 24-volt DC to a receiving terminal in the RTU's output section, which makes a high reference available for the output 3-bit represented on RTU terminal 13. The signal from RTU terminal 13 runs to RTU input terminal 1, representing the RTU's input bit 1. The RTU sees low reference voltage at terminals 5 and 10 connected to DC common. That's all there is to cover for project wiring. Now I'll describe one technological alternative to the tools I used for this project. As I covered in the function section of this video, the field devices and OPC server communicate using Modbus TCP protocol. A student working on this project in the future could also consider using DNP3, which is a newer protocol with improved features that are tailored to electric and water utility environments. According to Wikipedia, DNP3 does not use polling to communicate. For example, field devices can send event-driven messages, such as input updates, in live time without waiting for a poll from a master device. You probably noticed some lag between commands and state confirmation in some of my live HMI segments, so DNP3's quicker communication would have been helpful to reduce that lag. Though there are quite a few options for field device communication in general for electric substation devices, the only options that are configurable on the equipment in this project at MTC are Modbus TCP or DNP3. So DNP3 is the protocol to try for a student who wishes to expand their familiarity with modern communication protocols. That concludes my discussion about my project's administrative topics. At this point, you've learned about some of the risks in an electric substation, the workflow to set up Modbus communication between field devices and an HMI via an OPC server, an example of the network topology for a basic electric substation, and some of the HMI functionality to run an electric substation. For those of you who are considering your future career, you also have an idea of the kind of knowledge you can gain in an associate's degree program for automation technology. I hope you found this video helpful. Take care.